Hello and welcome back to Calculus 3. Not a section number, but exam number 2 review. Now you picked to have an exam next week on Monday, I believe. I'll show up, okay? And you have your quizzes going. So far, one quiz has passed, I believe, only yesterday's quiz. There is one. Quiz 2 is due tonight, right? At midnight. So if you're watching this early enough and you forgot about quizzes, then you missed only one. We are focusing on chapter 12. But then you can add anything else that you want from chapters 11, 10, chapter 6. Anyone? Anything? Sequence is a series, chapter 8. No? Yeah, chapter on power series. We can do that. Because, I mean, eventually you're going to go to differential equations and you're going to find that chapter 3 has a title, Solving Differential Equations Using Power Series. so yeah, it's going to be awesome. Chapter 12 deals with planes and surfaces, graphs and level curves, limits and continuity, partial derivatives, chain rule, and then approximation, like the linear approximation of a tangent plane, directional derivatives, gradient, and all that. So I'm going to write the list of all of these things. I'm also going to make sure that you know the formulas that are absolutely a must to know. We already discussed why we cannot have formula sheet in Calculus 3 because it makes no sense. If you get the formula sheet, then you're not learning any Calculus 3 because the formula sheet would immediately reduce it down to just mere calculations from Calc 1. So we are going to start with the concept of a plane, right? And I'll mention it again later. For honors, you need to know how to derive equation of the plane if you're given the 3 points, right? Using the vectors and so on. So we have plane. And then that will eventually go into tangent plane, right, when you marry this with your partial derivatives and so on. Then we have the graphs of level curves. And depending on the situation, I might have a shape with multiple choice formulas to match, or maybe a formula and 4 shapes, right, which I can produce in Mathematica and just, plug in. So pay attention to those problems where you have to match formulas to shapes and so on. You need to know the surfaces, and elliptical paraboloid and ellipsoid is watermelon, and write the cones, you know what the cones are. Hyperboloids are 1 and 2 sheets. And then the hyperbolic paraboloid, what's that? Saddle, thank you, saddle. So those are the ones that we had. Then we have limits, which branch into those plug-in. And does not exist. I'll just put does not exist. Use 2 paths. That's just standard stuff. Continuity. That's the same like in Calc 1, continuity at the point, right? The 3 rules. Then we have partial derivatives. Chain rule. Now, when I say chain rule, you need to be able to first get the tree and then compute. After that, we have directional derivatives and gradient. Must know the formula on that one. Gradient. Also, formula. It's a vector of partial derivatives. Easy. Now, also for the gradient, we know that we are looking for the steepest ascent and steepest descent and all that stuff. So that's all in there. And then here we go, tangent planes and linear approximation. So coming back to that. Tangent planes, then we have linear approximation and the differentials. Now that's formulas again. We have a min-max, again formula, and we have Lagrange, formula. You probably have 10 formulas, right? There is a formula for Lagrange where del f equals lambda del g. You have min-max formula, the second derivative test, where you have the fxx times fyy minus fxy squared, right, is either less than 0, equal to 0, larger than 0. And then you have the formula for the equation of the plane, right, with ax minus x0 plus b y minus y0 plus c z minus z0 equals 0, which actually turns into a tangent plane if you replace ABC with the partial derivatives computed at the point. So there's that formula. You have infinitely many formulas in chain rule, right? You draw the tree, then you can write the formula out. And which makes sense for me to say you have 10 formulas where you have infinitely many, right? Because there are infinitely many combinations that I can put for chain rule. You need to know how to get the tree. So gradient, again, I already said it's a vector of partial derivatives. Continuity tree rules, if you want to call that formulas, right? The point has to exist, the limit has to exist, and they have to be the same. You know that from Calc 1. Not that much new stuff. What are the pitfalls of the test? The biggest grade killer, slayer, whatever, obliterator is the unit vector u for directional derivative. Because, right, if I give you the direction of 1, 1, right, in the directional vector v, 1, 1, well, that's not a unit vector, right? Unit vector for 1, 1 is root 2 over 2, root 2 over 2. So you have to be very careful what you are using in the formula. The formula for directional derivative is going to be gradient times, right, dotted with the unit vector. Now, if I give you a vector 3, 3, 4, that's not a unit vector because the magnitude is not 1. And that is going to obviously get you the wrong directional derivative. It is very important for the vector to be unit vector because you want its magnitude to be 1 so that when you multiply that into gradient, you are not changing the magnitude of the derivative. You are not changing the size of the derivative, right? Because the derivative is 3, or derivative is 7, or derivative is 5, right? And only if you multiply those numbers by 1, they stay 3 or 7 or 5. They don't change the value. So you have to make sure that you are using unit vectors. So that's one of the great killers on the exam. Another great killer on this exam is not learning at all anything about differentials. I have no clue, but throughout the generations, so now I tend to put differential question on it because no one cares about it. So I just say, well, there you go. You can always replace it with something else, and then something else is going to be terrible too, so there you go. I don't know, just differentials are easier and less work than tangent plane that you have to first find and then use. But I don't know. So that's another great killer. Other than that, you know, also graphs, like not, because you don't have experience. First of all, you know, your pride that you are in Calc3 and that you are accomplished so far in mathematics, right? That you are in this top 1% of all of our students, in terms of math at least, gets you to the point where you really don't invest a lot of time to learn those drastically new areas, like graphs of 3D shapes. For me, it was much harder than for you. You have Mathematica. You know what that means? You want to sit in front of the screen for like 2-3 hours, keep plugging in stuff and changing to see what happens with the surface and what way it's going to look like, and so on. Test the formulas, right? Just to get the sense, right? To say, and then connect that to the world around you, right? You're looking at a cereal bowl. Well, that's maybe a half of the sphere. If it's not a half of the sphere, it's a little bit elongated or something. Looks like maybe upside down umbrella. Oh, okay, great. I know that's a paraboloid, right? That's a paraboloid, elliptical paraboloid, but it's a circle, so circle is special ellipse. Still fits. To look at those, right? Then to look at those roofs, right, that do this and realize that's a sine, right, going and stretched forever, and all of those kind of things. It takes time to, especially because it's so new, right? When you see the graphing for the first time, you see the linear line, and then you stare at that thing for 2 years over the multiple math courses that you take, and then you finally break away from that into, you know, quadratic and cubic and e to the x and all of this stuff in pre-calc, and then that's drilled more in Calc 1 and Calc 2, all of those functions, and then boom, Calc 3, right? Zero experience so far, and then, I don't know, motivation is not there because I guess you're not connecting it to shapes around you. Yet this class must be, you know, the easiest one because you live in the space of this class. Everything so far before this class, we said it's on the ground, right? This is our XY, and you walk on it, right? That's your previous stuff. But now you're getting the shapes that you can actually pick up, and you can compute the volume. No one cares about areas unless it's square footage of your house or you know how big your farm is or something like that. Like who cares, right? Areas are not that interesting, but the volume, right? You want to know how much luggage you can bring, right? And all of these kind of things. Create a box to put something in it and ship it halfway across the world in one piece. Okay? So, you know, these things, they actually produce jobs and meaningful things, especially the design for mechanical engineering and civil engineering and all of these kind of things. It's all 3D objects that exist in physical. You can touch them, you can size them up, compute things. So this is a very relevant class, and yet again, the most important concepts are overlooked, and that's the problem. Personally, I told you, I don't care about any of these things that are calculated by hand because we don't do that anymore. We have the equipment for it, but, you know, education being what it is. Yeah, unfortunately, you're stuck with those things. So those are the great killers. Again, graphs of 3D surfaces, differentials, and not using the unit vector within the calculation for your directional derivative. Those are the three major issues. The rest, obviously, if you don't know how to differentiate from Calc 1, I can't do much about that, right? Because the focus of this chapter here is differentiation. For most part, is differentiation, right? When it starts with partial derivatives, the rest of the chapter is all derivatives. So having the concepts, again, for min and a max, knowing that min and a max, it's each partial derivative set equal to 0, and then go from there, right? Those are all important concepts. I listed the formula. Now, honors, right? I'll add this here, honors. We have a few proofs and derivations that you guys must know and must be able, and that's first one is to derive equation of the plane. So not necessarily tangent plane, but the plane in general. That's in the very first lecture. I did it in class, and it's also in the textbook. So that's one of the things for honors. The other one is to have the definition of the derivative, right? The derivation using the limit is the same like in Calc 1, except you just put comma age. So limit definition of the derivative to derive formula for partial derivatives. This is in section 12.4. Also directional derivation. And is there anything else there? I think that's it, except let me just check in 12.8. I think there's one concept that you can also look at, and that would be so critical point. Oh, great. They do talk about it. So Hessian matrix, this is the page 941. So just, you'll know when you read it. You can also go online and look up more stuff about that, like math.org or something. Good. That's the list. Questions, concerns, problems to solve? Yes.
About honors, like
two problems
no,
at the end of the
not about that. Like, I mean, like for reviewing, like the notes aren't on like lines then, so like.
We moved to Google Docs a month ago.
Oh, so have you posted the 12.8, 12.9 notes?
No, I will now.
Yeah, that's
So the reason why I didn't post the 12.9 was, well, I don't know what 12.8, but 12.9 was because it was two separate lectures, and then with all the snowstorms we had, we canceled 2 classes, right, back to back in 2 weeks, and then the spring break in between. So, yeah. So I saw you twice in 3 weeks. That's how terrible the entire month was, right? I saw you twice in 3 weeks. So if we could have this stupid spring break to be just erased from the existence, it would be very beneficial for everyone. All right, good. So your question answered. Any problems, questions to work on? Yes?
All right. It's a max-min problem.
It's a max-min problem.
Well, it's more or less a critical point problem.
Critical point problem. Let's take a look at the critical point problem.
We'll say your function is equal to negative 4xy minus x to the 4th minus y to the 4th. You're going to try to find the critical points for that.
Try to find critical points.
Not try, but find the critical points for that.
I'll try.
And if so, then list the points.
All right. So we need the fx. And fx is going to be negative 4y minus 4x cubed. And we need to set that equal to 0. Now, clearly, we can't solve it because then we have a fy, which is going to be negative 4x minus 4y cubed, also equal to 0. And we can't solve it by itself. But together, we can solve these, right? Now, do you see the symmetry? The symmetry of these equations suggests that x is equal to y, because you can swap x's with y's, and if you swap x's with y, you get the other equation, right? So x equals y. When the equations are like this, they are the same coefficients, same signs, same exponents, same everything. And if you are able to swap x and y and get the other equation, that's symmetric, right? In which case, that implies that x is equal to y. Now, from that point on, pick any of the equations and just run it as all x's or all y's. So if I pick the first equation, it will be negative 4x minus 4x cubed equal to 0. I'm going to factor out negative 4x and then have just 1 plus x squared equal to 0, from where I'm getting x equals 0. And then y is 0 as well. And the critical point is at 0, 0. And then also 0 at the end, because when you plug in all the zeros in the original function, you get z is equal to 0. So origin is the only critical point for this one.
Because I had a problem like that was on the quiz yesterday, but not only I had the origin part, but it also had like 1 comma negative 1 and negative 1 comma 1. That's how I was confused. I had no idea how I got that.
Well, probably one of the signs was different because I don't like this one, right? So by changing one of the signs or two of the signs up there, that would give me 1 minus x squared, in which case I will also have negative 1 and 1. In this case, 1 plus x squared has roots as negative I and I, and that's not real, so...
No, that was the exact problem that I had, because I wrote it down. Yeah, negative 4xy minus x to the 4th minus y to the 4th. So that's why I was confused why that was it.
Well, could be a glitch of some sort. Diego has something. Is that different problem? Okay.
Absolutely. That's my name.
Okay, I'll do it. I have to write it. I'll give it back the paper. I promise. I promise. I won't leave with your paper. So Mike, would you try to play with the signs up there?
Okay.
And see? Well, no. Technically, what I'm seeing is just make this one positive over here, and if you redo the whole problem, it should give you a negative in the parenthesis. Yeah. And immediately you are going to get those answers. It could be a glitch of some sort, I would say. Another problem, in this case, for absolute min and max. Now, we don't get to do only this. We actually have to also look at the edge of the problem. So we have f of xy given as 5x squared minus 10x plus 7y squared plus 49. No, plus 9. And we also have the region. And the region is a circle. So region R of all points x, y such that x minus 1 squared plus y squared is less equal than 1. All right, so our method is going to detect all of the points inside the object. So let me give you, again, here's the squirt bottle, right? And the shape of this squirt bottle over here is given by the function f of x equals to 5x squared, blah, blah, blah. All right, so that's this shape. Now, this shape, actually it's better if I use the bottle. I'm going to borrow a bottle for a second. Better. So here it is, right? So you're looking at this shape, right? And you see that here is the max, right? Now you also have a circle in the bottom, which is this guy, right? So this is a perfect representation for this particular problem. It looks like this. Now, maximum on top could be anywhere. Could be in the middle, like it is on this bottle, but imagine me taking a sword and cutting it like this. Where would the max be? It would be at the edge, right? Which means it will be on this line, which is intersection with this thing over here. So we can have multiple situations, right? Multiple situations. And we could have multiple max values, right? We could have, like if I am to squish this top inside so that as I'm pressing down, this passes and gives me the ring over here, and at the same level, the indentation of the cap. So I just squish it in, right, to the point where it's flat, right, but all of the plastic bent inside, and then the top is at the same level. So now I have a maximum all around the ring, and then the top is as well in the middle, right? They're all the same max. So we have two procedures to worry about here. It's the standard procedure that we know, first partial derivative, second partial derivative, do all of that kind of stuff. And then also look at the edge and find out if there are any max values there. So let's go fx. That's 10x minus 10 equal to 0, x equals 1. Perfect. Fy is 14y plus 9 equal to 0. X equals negative 9 over 14. Not so nice. So that's y. So we already have a critical point at 1, negative 9 over 14. Oh, yes, you're right. Derivative of 9 is 0. So y is equal to 0. Thank you. So it's 1 and 0, and you can immediately compute z. Great, thank you. So that's 1 minus 10, that's negative 10, and then the 0. So I think negative 1, right? Again, when I plug in 1, I get Oh no, I get 5. What am I talking about? I get 5 minus 10 plus 9. That's 4. That's a 4. So 1, 0, 4. So that's our point. And now, what is it? Is it a min, max, or a saddle? Well, calculate fxy. Sorry, fxx first. Calculate fxx. fxx is 10. Calculate fyy. fyy is 14. Good. And then fxy, 0. So now we can calculate d. d is 10, not 10 squared, 10 times 14 minus 0 squared, which is 140. Now that's bigger than 0, right? For the bigger than 0, we can have a min or a max. And when it's less than 0 is a saddle. So now we also have that fxx is positive. So it's a min. So we know this is a minimum. You have to memorize the combination, right? The fxx positive and d positive minimum. fxx negative and d positive is a maximum. And d negative is a saddle point. And if d is equal to 0, the method is inconclusive. You have to use something else. So far, we dealt with the inside. And I found the minimum point at 104. Now we have to take a look at the edge. So what do I have? Well, I have the ring, the disk, on which gives me the edge. And that disk is x minus 1 squared plus y squared. I'm just going to call it equal to 1. From here, I can solve for y squared, and I will get 1 minus x minus 1 squared, which I can further expand into 1 minus x squared, minus in front is plus 2x, and then plus 1 minus 1. So this thing is actually 2x minus x squared, right, when you simplify everything. I also have my function f of xy, which was 5x squared minus 10x plus 7y squared minus 9, right? Plus 9. Thank you. So now what I'm going to do is I'm going to plug in. And then as soon as you plug in, you killed your y's, so this becomes f of x function. So I have a 5x squared minus 10x plus 7 times 2x minus x squared plus 9. And then you have to crank Calc 1 procedure. So now I have negative 2x squared, right, because I have negative 7 over there. I have a positive 14 minus 10, so it's a plus 4x, and then plus 9. We find the derivative of that, which is negative 4x plus 4 equals 0. We get x equals 1. So we're doing Calculus 1 procedure now. So if I have x equals to 1 as a critical point, right, x equals to 1, I can now just figure out whether that is min or a max using the Calculus 1 procedure, test point 0, test point 2. F prime of 0 is 4, which is larger than 0 means increase. And f prime at 2 is negative 8 plus 4, which is negative 4, which is less than 0, which means decrease. So I have a max there. Right? So x equals 1. I can compute y. So y squared is going to be 2x, so 2 times 1 minus 1 squared, which is 2. So I have that y is equal to plus minus root 2. Oh, minus 1. Thank you. Yes, yes, yes. Yes, because good. Thank you. So now I have 2 points. I have 1, 1. I need to calculate z. And I also have 1, negative 1, and I need to calculate z. To calculate z, I go back to the original function, which I have right here. So that's going to be 5 minus 10. That's a negative 5 to 11. So this one should be 11. And we know it's a max. And then have the negative 1 plug in. So that's a 5, 15, 22, 31. Oh, that one is bigger. So this is the ABS max, because that's the higher than the other max. Other max is at 11. Just, guys, you can imagine this very simple. Just put 3 people here, arrange them in a triangle, all right? 3 people, cover them with a big sheet, right? And you will see, because they're all different height, right? Some of these stick more out than others. That's what this is, right? You have some kind of surface. Where the microfiber cloth? There it is. Right? So you have 3 points, right? And there we go. And when I put this thing on it, right, you see that this one is sticking out the most. That's that one. Then there's one that is less sticking out. That's that one. And then you have the other one. Well, the other one is a minimum, so that will be the one in the. So maybe it's this way. I don't know. You have a minimum there. You have one that sticks out more and one that sticks out less. Now, do you really want to understand this? Just graph the damn thing in Mathematica and look at it, right? Because you have Mathematica, you have Desmos. I don't care what you use, right? If you really want to see these things, because these points, they exist, right? They exist. So you just look at the shape, and it will be clear. This one sticks there, this one sticks there, this one's the minimum, and you can see them, right? Because you know what the minimum is, right? That's the minimum, right? That thing in there, that's the minimum. And these guys over here are maximum, and you have absolute one that is the highest, and you have relative ones, the rest, the smaller ones. And that's that. Good. So, 2-part question. If there is word absolute min, absolute max, that means that I have to test everything, right? The part 1 is just the regular stuff that we do, but we are testing inside, right? And we found the minimum. And then the rest is the edge calculation. In this case, it worked out to have 2 max values there, and absolute max is the 31 one. Yes?
Can you scroll up a little bit on the question about like the first part of that problem? So I had a question where, like, when you find the partial derivatives,
Yeah.
if you have like an x and a y in like...
You solve system of equations.
Okay.
Yes. So we had that in a previous problem. I wasn't solving system of equations. I could have. I wasn't. Because I exploited symmetry.
Right.
But if you end up with the equations that you can exploit the symmetry and they're vastly different and they have x's and y's mixed systems of equations, because it's a common point for the derivatives. Anything else? Going once, going twice. Solved.
You never rolled dice.
We will. All right. Bye.